Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been going through several modules in this course, as we have seen before, like we have had an overview of power electronic converters, and we looked at the voltage source converter, different applications of voltage source converters such as motor drives and power quality, active front end converters and so on, and we looked at modulation at low frequencies. Then we have been looking at modulation at higher switching frequencies, that is the switching frequencies being much higher than the modulation frequency, and we looked at how do you produce PWM waveforms based on triangle comparison, and how do you do it based on the so called space vector approach. And we also saw that there are some advanced bus clamping PWM methods which are possible, especially with the space vector approach. And after that we were focusing on line current ripple in the last module. That is, in the PWM inverter you have a DC voltage and you have certain modulation index, and that produces certain amount of AC voltage. But what happens is it does not produce only the AC voltage, it produces certain harmonics also, and we were looking at those harmonics. We looked at them in one lecture in the frequency domain point of view, like we looked at the harmonic spectra, and then in the subsequent lectures we were trying to evaluate the RMS line current ripple. Let us say in motor drives fed from voltage source inverter, you may have a sinusoidal current, and not only that, on top of the sinusoid you may have some ripple current. We were trying to estimate that RMS line current ripple. So, we were kind of into the space vector here for generation, PWM generation, and then we were into the space vector domain for analysis here. Now, and we were also focusing in the previous module more on the harmonic distortion and such aspects, and we would continue that in a later module on analysis of torque ripple, where in the last module we analyzed line current ripple. We will have a subsequent module on torque ripple, which is in some sense related, and we will look at more of that now. Right now what we do is we take a break and we look at things which are more fundamental, in the sense we would look at the relationship between the AC side current and the DC side current, and the AC side fundamental currents to be specific, and the DC link current. So, this module is going to be on the analysis of DC link current. So, in all the previous modules when we were looking at how do you produce the PWM waveforms and what is the PWM waveform and what are the harmonic components and things like that, our focus was entirely on the AC side, but now it is moving to the DC side. So, we are just going to see why it is that now, right. So, we will see some kind of how the DC link currents and the line currents or the AC side currents are related among the various things in this one, and we will work out a mathematical model for a PWM inverter. Let us say you want to solve an inverter using a like an equation solver package, you want to do some simulation. So, you need a simple model. We will try to come up with a simple model which you can use in an equation solver to solve that, and we will define switching functions for the 3 phases, and we will relate the DC voltage switching functions and then the AC terminal voltages, and then we will look at the relationship between AC terminal voltage and AC side currents. Essentially these are related in terms of the load, and then with the AC side currents and the switching functions, how to derive the DC link current is what we are going to see, and we will look at both the instantaneous and the average values of DC link current. So, at any particular instant there is certain amount of current flowing through the DC link, that is the instantaneous DC link current, and that can be averaged over a half carrier cycle or a sub cycle, and that is what we call as average DC link current. It is same as what we used before, average pole voltage, average voltage vector, average current, and all those. It is similar to that. Now, we are going to be looking at the average DC link current also. In this module we will also look at the DC capacitor current. So, what is the amount of current that will flow through the DC capacitor? So, in the DC link current we will have a DC component which flows from the mains, and it has a ripple component which primarily flows from the DC capacitor. So, that is something we will probably look at in the next lecture, but as part of this module, and we would get an understanding of DC link current in this now. So, this lecture is particularly titled instantaneous and average DC link current in a voltage source inverter. You know a voltage source inverter. The voltage source inverter has a DC side and the AC side, and this is the DC side current that is flowing into the 6 bridges here, and what is its instantaneous value and how do you evaluate its average value? That is primarily the question we are looking at in this particular lecture now. So, this is the voltage source inverter, just for you to take a relook at. These are the DC terminals, and these are the 2 switches, and in every leg, if the top is on, the bottom will be off. If the bottom is on, the top will be off. So, you know that everything is like a single pole double throw switch. So, what we are trying to do here is these are currents we can define them as, let us say, IR, IY, IB. These are the line currents or the AC side currents, and this is what we are calling as the DC link current, IDC. This is what we want to do. So, generally, in many situations I found that students are also more comfortable coming up with this, the AC side current, because in an inverter the DC voltage is fixed, and then if the modulation signals are given or the PWM signals are given, it is easy to define the 3-phase terminal voltages, and then if you have a proper load model, you can predict the 3-phase currents. So, students are generally very comfortable predicting this 3-phase currents, but I found them often having some difficulty in doing this DC link current, and this is very important from certain other points of view also. So, why is DC link current important? So, let us say there is this, the DC link current, there is some power supply which will primarily provide a DC component. Now, this DC link current also has a ripple component, and that will be supplied by the capacitor, which I call as I cap now. So, this I cap is also very important. That is one of the reasons why you should do this is, you should know what is the RMS value of this. In sizing the capacitor, there are two things. One is you have to make sure that you have big enough capacitors such that the voltage ripple is very, very small. So, that depends on the value, depends on what is there on the DC side, whether you have rectifier and all those issues also. So, but in general the philosophy is the value of C should be chosen such that the voltage ripple here should be very small, excuse me. And the next rating of important rating of a capacitor is its RMS current. You have to make sure that the capacitors have enough RMS currents that are chosen here now. So, that in that sense also it is important now. More importantly, we are now looking at it just from the understanding of the voltage source converter. We are doing this exercise firstly to get a better hold over the voltage source converter, get a better understanding of voltage source converter, and we will also use this idea to come up with how to evaluate the capacitor current. Alright. So, the kind of load we have been assuming is a 3-phase load R, Y and B, and it is a balanced 3-phase load. This neutral is not connected to any other point electrically other than through the line terminus. So, this R is connected, Y is connected, B is connected. So, it is a 3-phase 3-wire load, as I have mentioned before. This is the kind of load we have always been considering in this course now. So, let us define the switching functions now. See, there are 6 devices, they are on, they are off, they are on, they are off. No, there is some way they have to be represented now. So, they can be, that is one convenient way of representing them as switching functions now. We can define switching functions, 3-phase switching functions SR, SY and SP. These are actually digital signals, they can take the values of just 1 or 0, and SR is equal to 1 if R phase stop device is on, and SR is 0 if R phase stop device is off or the bottom device is on. That is all. They are, it is a complementary logic between the top and the bottom. So, the top is on, the bottom is going to be off and vice versa. So, SR is equal to 1 if the top is on, SR is equal to 0 if the bottom device is on, and similarly SY is equal to 1 if Y phase stop is on, and SY is equal to 0 if Y phase bottom is on. Similarly, you have SB is equal to 1 or 0 depending on whether the top device is on or the bottom device is on. So, you have the 3-phase switching functions which have now been defined now. So, with these switching functions you can define on the DC bus voltage, you can define what are your voltages now. So, you have the switching functions as we defined before, and then let us say you have the pole voltages. The first thing you have to come up with pole voltage, that is the voltage at this pole R with respect to O. So, what is that going to be? When the top device is on, that is when SR is equal to 1, the pole voltage is going to be 0.5 VDC. So, this is going to be SR minus 0.5 VDC. So, when SR is equal to 1, it becomes VDC by 2, and when the top device is off or the bottom is on, SR is equal to 0 and that is equal to minus 0.5 VDC. Therefore, the pole voltage VRO can be expressed in terms of SR and VDC like this, SR minus 0.5 VDC, and VYO can be written as SY minus 0.5 times VDC. Similarly, VBO can be written as SB minus 0.5 times VDC. So, given the DC voltage and the switching functions SR, SY and SB, it is possible for you to write down VRO, VYO and VBO. Next, you have the line to line voltages here. So, you have VRY. What is VRY? It is VRO minus VYO, and similarly VYB is VYO minus VBO and VBR is VBO minus VRO. So, you have the pole voltages and line voltages are defined like this now. We are slowly evolving a mathematical model. If you are going to simulate, voltage source inverter, what you can do is you can assume all the devices to be ideal and you have their DC bus voltage, and then you can start with the switching functions, and the switching functions you can generate them easily, for example, by comparing a sine and a triangle or whatever, whichever way is suitable for you, we can do this now. So, start from the DC voltage and the switching functions fed for these devices, you can start saying what are the AC side voltages. So, now we have come up to the line voltages. Now, let us go to the line to neutral voltage. We have said it is a 3 phase balanced load, star connected load. In this kind of situation, it is possible to say that VRN is VRY minus VBR by 3. Similarly, VYN is VYB minus VRY by 3. Similarly, VBN is VBR minus VYB by 3. So, we have discussed this even earlier now. Thus, you can reach up to VRN, VYN and VBN now. So, the 3 phase voltages applied on the load are available. Let us assume an RL load just for the time being and just as an exercise. Then you have VRN is equal to the resistive drop plus the LDI by dt. VYN is equal to similarly RY plus LDI by dt, and VBN is equal to RIB plus LDI by dt. So, this would be your load equation, right. So, you have to solve the load equation. How can you solve the load equation? You can rewrite this as DIR by dt is VRN minus RIR by L. So, and this you can integrate now. What you do is, let us say you have VRN, and this VRN you can subtract IR from here. You subtract, and that will give you LDIR by dt. You divide it by L, you get DIR by dt, and you integrate that. This will give you IR. You can multiply this by R. Get this now. So, this is how you do that now. When you want to solve the equation something like this, you do not do a differentiation, but you would reconvert the problem into one of integration, and you basically use an integrator as shown here and do this now. So, this is a first order equation, and you require a single integrator to that. You can solve this similarly. This is how you go about solving now. If you solve them, what are you going to get? You are going to get IR, IY and IB. So, now with IR, IY and IB, you have to find out IDC. That is the next step. So, let me say this is IR, this is IY, this is IB. That is starting from the DC voltage and the switching functions. You have determined the 3 phase voltages VRO, VYO, VBO, or VRY, VYB, VBR, or VRN, VYN, VBN. And from the 3 phase AC voltage, you have come up with the 3 phase AC currents are also available IR, IY, IB. And now, what is that? All that now the next step for you is to find out what is IDC. As you can very clearly see, this is just KCL. It is the sum of these 3 currents here. Now, the question is what is that current? The current, as I have indicated here, can take 2 different values. One is it can be equal to IR if the top device is conducting, or the current can be equal to 0. So, you can say that the current here is SR times IR. So, when SR is equal to 1, it is IR, when SR is equal to 0, it is 0. And similarly, you can say that this is SY times IY, and what is this current? SB times IB, and therefore, your IDC is simply the sum of these 3 quantities SRIR, SYIY, SPIB, and it is just KCL, Kirchhoff's current law, you get IDC, right. So, this is what is indicated here, IDC is equal to SRIR plus SYIY plus SBIB. So, you have the DC link current available in terms of switching functions and line currents. Okay. Now, let us say we move on. This is just an instantaneous relationship. We have come up with a mathematical model for that. If you go back from one to the other, that is initially what we did, we are taking a voltage source inverter like this, and this is a 3 phase 3 wire balanced star connected load. We are assuming like this 3 phase 3 wire load, and we have defined the switching functions SR, SY and SB like this, and with this, with the switching functions on the DC voltage, we write the 3 phase pole voltages like this, and then we write the 3 phase line to line voltages as I have shown here. And from here what we do is you can write down the 3 phase line to neutral voltages as I have shown there. So, these are the different up to this you come to the AC voltages. Once you have got the AC voltages, you require the load model. Now, considering an RL load, you can write down the 3 phase equations for the load and you can solve them, and you by solution gives you IR, IY and IB. And once you get your IR, IY, IB, you can multiply them respectively by the switching functions SR, SY and SB, and you can add them up to get your DC link current. So, this kind of gives you a whole picture of what is required, and most part of to simulate an inverter, for example. Alright. The only other thing that you have to do is actually divide the current between the capacitor and the input, which we will do it later. And so, this basically relates the DC link current and the 3 phase currents for you. And so, now with that model what we try to do is, let us say the PWM inverter is being switched using space vector modulation. As we have been seeing in the last several lectures, space vector modulation basically means the voltage vector is a voltage vector is provided instead of 3 phase voltage references, and the voltage vector has certain magnitude Vref, and that is proportional to the desired fundamental voltage, right, and it is revolving at a constant frequency, and its frequency is the modulation frequency, is the desired modulation frequency, and this is sampled, and every time you sampled once in a subcycle Ts, and within that you do a time averaging. You apply the active vector 1 for T1 seconds and active vector 2 for T2 seconds, and you apply the null vector for the remaining time, and you produce this quantity now. And these are how to calculate T1, T2 and Tz. That depends on the values of Vref and alpha, and this is how we do it, as we have been looking at in the last several lectures, right. So, now what do we do? Let us say try and relate the DC link current and the inverter state. So, at any instant of time, the R phase has some switching function, either the top device is on or bottom device is on, SR is 0 or 1. Similarly, Y phase, SY is 1 or 0, the top device is on or the bottom is on. Same case about the SB also. So, now what you are going to do? We are going to look at the inverter state and then try to relate what is the DC link current. How do we do that? Alright, maybe it may be worthwhile to look back here. So, now if you see, if you take a case SR is also 1, SY is also 1, SB is also 1, what happens? All the 3 top devices are on and the bottom devices are off. That means an inverter state plus plus plus. So, in this case what happens? IR plus IY plus IB, and that will be equal to 0, because that is what is flowing to a 3 phase 3 wire load. Therefore, IR plus IY plus IB is equal to 0. So, in the inverter state, in the 0 state, when the top devices are all on, it is 0. What happens if all the bottom devices are on? SR is 0, SY is 0 and SP is 0. So, whenever the inverter state is 0, IDC is 0, and this is what we mentioned at the time we were defining 0 state. What is 0 state? It is a state of it is one of the states of the inverter where there is no connection between the DC side, there is no power flow between the DC side and the AC side, that is IDC is equal to 0. That is what we meant. Alright. So, we look at the inverter states one by one and write that down. Let us see this here. Okay. So, in this case, let us say if you consider the 0 state minus 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 R plus plus plus, you have IDC is equal to 0, as we established just a while back. Now, if you take the inverter state plus minus minus, what happens? You have a case where SR is equal to 1, but SY is equal to 0 and SB is also equal to 0, and therefore, your IDC is simply equal to IR. IDC is equal to IR. What happens when you are talking of the inverter state plus plus minus? You see it is plus plus minus. So, SR is 1, SY is 1, SB is 0. Therefore, in this case you have IDC equals IR plus IY, IR plus IY, which is also equal to minus IB. So, when your inverter state applied is plus plus minus inverter state 2, then IDC is equal to minus IB. Let us do a similar exercise for 3. So, only SY is equal to 1 in this case, and therefore, you have IDC equals Iy. Then how about inverter state 4, this is Sy is equal to 1 and Sb is equal to 1 and Sr is equal to 0. Therefore, you have IDC equals Iy plus Ib, and what is that equal to? Minus IR. Alright, then there are only 2 other inverter states left, this is 5. So, only Y alone Sy is 1, therefore, you have IDC is equal to, I mean it is Sb is equal to Ib, and similarly here these 2 states are high, then the top devices are on. In this case, you have IDC equals IR plus Iy, is that right? I am sorry, IR plus Ib, which is equal to minus Iy. So, the picture is complete. So, when the 0 states are applied, IDC is equal to 0. When the active states are applied, it is equal to one phase of the current or the negative of that. Here you see IDC is equal to IR. When inverter state 4 is applied, IDC is equal to minus IR. Similarly, when inverter state 3 is applied, IDC is equal to Iy. When inverter state 6 is applied, IDC is equal to minus Iy. Similarly, when inverter state 5 is applied, IDC is equal to Ib, and here it is equal to IDC is equal to minus Ib. So, you can also relate to this now. This is really the positive peak of R phase, this is the negative peak of R phase. This position stands for the positive peak of Y phase, this is the negative peak of Y phase. Similarly, this is the positive peak of B, this is the negative peak of B. So, you see that there is also a correlation there now. So, we have now tried to relate the DC link current in terms of the inverter states. So, let us go forward. So, this is the instantaneous current, and what do you mean by the average current? How can we calculate the average current? So, what happens within a inverter state? So, within a subcycle. So, let us say we have a subcycle, and in that subcycle you have inverter states. Let me say you have states, this is the subcycle duration. Inverter state 0 is applied here, let us say the inverter state 1 is applied, 2 is applied and 7 is applied, and this is the whole duration Ts. So, this 0 means all of them are negative, 1 means plus minus minus, 2 means plus plus minus. Let us say this is the this is what is applied in one inverter cycle. So, this is for duration T1, this is for duration T2. So, now what happens? You have 3 phase currents. In this subcycle, you will have 3 phase currents. So, what are their values? It depends on the power factor also. Now, let me say this is my IR, this is my IR. Let us say this is my IY, and this is IB. There you can consider them to be constants over the subcycle, and you can ignore the ripple, because for all this purposes the ripple, if you consider it is much smaller than the fundamental, you can take this as the fundamental component IR1, IB1 and IB1. These are the values of currents. So, what do you have? You are looking at what is the DC link current at every particular this thing. So, the DC link current is, let me use a different color. During this interval, the DC link is 0. During the last interval also, the DC link current is 0. This is IDC. Why? 0 states are being applied. Now, you have this. We know what is it that. What is that equal to? That is equal to IR. So, this current is equal to IR. And how about the next interval T2? It is going to be IR plus IY, or it is minus IB. So, this minus IB is something like this. This is minus IB. and the rest of the time is 0. So, this is the nature of variation of the DC link current over a subcycle. So, this is how it varies over a subcycle. So, when 0 is applied, this is when 1 is applied, when 2 is applied and when 7 is applied, and this has certain average value. What is that? Some average value like this, some average value. And how much is that average value? Let us call this as IDC average. What is that IDC average? That is equal to whatever is your instantaneous IDC, and let us say dt integrated over 0 to Ts divided by Ts. It is the average value over a carrier cycle. And what is that equal to? That is equal to IR1 multiplied by T1 plus, or rather minus IB multiplied by T2 the whole divided by Ts. Now, this is the average current now. This is the average DC link over that now. So, what will happen from one cycle to another cycle? Instead of 1 you go into the next cycle, what is going to happen now? Your IR1 value will change and minus IB will also change, and the T1 and T2 values will also change. So, the DC link average current will go on changing from one subcycle to the other subcycle, and this is the case we have considered in sector 1. And then if you go to another sector, you will see a similar picture, and which we will just do in a short while now. So, what you will see is, you will see that it actually repeats over every sector, as we will see a little later now. So, let us say we are looking at the average DC link current over a subcycle in different sectors. So, that is now the earlier one we looked at sector 1, where you use the active state 1 and active state 2. Now, let us say you do differently, let us say in sector 2 now. So, let us say if you want to do it in sector 2, okay. So, what am I doing? I am considering some subcycle, and let us say the inverter states are 7, 2, 3, 0 in what is called as sector 2. That is, you have the other region in your plus minus minus, plus plus minus, this is minus plus minus. This region is sector 1, this region is sector 2. So, we are going into sector 2 now. So, here the inverter state is plus plus plus, the inverter state is plus plus minus, the inverter state is minus plus minus, this is minus minus minus. If you are going to do it like that, so let us say what are the 3 phase currents now. So, we are in sector 2, and you can see that in sector 2 your R phase has got a 0 crossing. So, you may have a R phase current which is like this, this may be your R phase current, this is IR, I can call it IR1, the fundamental component, we can ignore the harmonic component here now. And let us say we go to IY. So, IY will be somewhat positive now. This is the Y phase fundamental current now, and then let us say we look at the B phase current. This is IB. So, now these are the 3 phase currents, these are the 3 phase currents now. So, when I want to draw my DC link current, what I can say is during this time it is 0, this also it is 0. Here I am drawing the DC link current. Then what happens during 2? It is IR plus IY. This is IR plus IY. Here it is IR plus IY or minus IB, and here what it is? It is equal to IY. This is IY. So, this is the nature of current during that, right. So, if you take two instants which are 60 degrees away, let me just show that here. If you take two instants which are 60 degrees away, like here, this is Vref, that is Vref, the same value of fundamental angle, the angle is 60 degrees. Then what will happen is, you take these two cases, this duration, you will have a switching sequence like this. This duration T1 and T2 will be equal to these durations T2 and T3. And similarly, these currents what are IR and minus IB, they will be equal to what are IR plus IY, that is minus IB, and what is this IY. So, let me just write this down also. This is IY, this is minus IB. So, you can see that in a 60 degree time things change. It is IR is so much. So, 60 degrees later minus IB will have the same value. Similarly, here minus IB is so much, 60 degrees later IY will have the same value. Please remember, these are all we are considering only the fundamental components, and the harmonics are very small. If you assume the peak to peak ripple current is small, they are all negligible now. So, what do you get? You see that the same pattern of the DC link current ripple repeats here and there. This and this, what I have drawn in green and what I have drawn here in red. This is sector 2, this is sector 1. Both of them are the same. If you are considering one subcycle in sector 1 and another subcycle exactly 60 degrees away in sector 2. So, this DC link current has a periodicity of 1/6 of the fundamental cycle or just one sector. So, that is the periodicity of that, and when you want to evaluate this DC link current or its average value, you basically can just look at evaluating over one sector. That is one good way of doing it now. So, this is what we have now come to. So, we can just start going into the expression for an average DC link current now. Let us start writing down an expression. So, what did we find? Let us say taking the case of sector 1, any sector you can consider. Let us consider the case of sector 1. So, we found that this IDC average that is equal to IR1, that is the R phase fundamental component, multiplied by T1, that is the time for which the active vector 1 is applied, then minus IB comma 1, which is the fundamental component of B phase current, multiplied by T2, and the whole thing divided by Ts. Why are we doing like this? When the 0 states are applied, the DC link current is 0. When the active states are applied, when active state 1 is being applied, that is applied for T1 duration, and the DC link current is IR1. When active state 2 is applied, it is applied for duration T2 seconds, and the DC link current is minus IB1. Therefore, IR1 multiplied by T1 minus IB1 multiplied by T2, the whole thing divided by Ts, and you will see that in this case IB1 is negative, and therefore, minus of IB1 is positive. So, this is what you have. So, you can go ahead like this, you can evaluate this now. So, can we write expressions for this? How do we write expressions for this? That is the next question now. So, we can reproduce some of the older expressions that we have had, and we can write correspondingly new expressions. What can we do? This is IR1. What is that? That is the fundamental component. How can you write what is the fundamental component? Let us say you have the fundamental has some peak value Im, and that is going to be sin omega t plus phi, which is phi is the power factor angle. Similarly, you can say IB1 is equal to Im times sin of omega t minus 240 degree or plus 120 degree plus phi. So, you have them. So, what are this? Im is the peak values of the fundamental currents, omega t gives the present instants, omega is the angular frequency and t is the present instant of time. So, we are considering omega t in the range 90 less than or equal to omega t less than or equal to 150 degree. This is the range we are considering. This is sector 1. So, sector 1 starts from the positive peak. This is the positive peak of R phase fundamental voltage and this is the negative peak of B phase fundamental voltage. Sector 1 extends from the positive peak of R phase to the negative peak of B phase, and this is what you have now. This can be substituted. What else? Then you have T 1 and T 2. What you can do about T 1 and T 2 is you can write similar expressions. T 1 is what? Is V ref divided by VDC times sine of 60 minus alpha divided by sine of 60 degrees multiplied by Ts. And what is T 2? T 2 equals V ref divided by VDC sine of alpha divided by sine 60 degree multiplied by Ts. So, you have T 1, you have T 2. So, now next what you can do? You can try multiplying all of them and do this now. So, there are a few issues now. What are they? What is Im? Is the peak value of current. What is Vref? Vref is the magnitude of the fundamental, I mean it is the magnitude of the reference vector and that is related to the fundamental voltage. How is it related to the fundamental voltage? If you recall our earlier discussions based on our space vector definitions and so on, Vref is equal to 3/2 times the peak value of the fundamental phase voltage. It is peak value of fundamental phase voltage now. And so, this is Vref and here you have omega t and here you have alpha, and this relationship also I can quickly write down. So, now you are in sector 1. In sector 1 whatever is your alpha, omega t is equal to 90 degree plus alpha is the relationship between omega t and alpha in sector 1. Further, V reference is equal to 3/2 times Vm, where Vm is the peak phase fundamental voltage. This is the peak phase fundamental voltage. So, when you substitute all these quantities, you will get you can kind of deduce an expression for the average current. Let us just do this one more step in the following one, right. So, let us say we want to do IR1 T1 minus IB1 T2. So, what do we have here? We have IDC average is equal to IR1 T1 minus IB1 T2 divided by Ts. Here you have V reference for T1 and T2 and V reference is 3 Vm by 2. Then you have Im here. So, this is Im which is common here and again Ts is common. So, what I can see is divided by Ts and you also have divided by VDC, that is 3 Vm, you have Vref by VDC which is 3 Vm by 2 times VDC and Im is what is common between IR1 and IR2. So, you have taken Im out there, you have divided by Ts and what else there? There is also a factor of sin 60 degrees, 1 by sin 60 degree. And now, what I have is from IR1 I have sin of omega t plus phi, that is multiplied by for T1 you have sin of 60 minus alpha. Then for minus IB you have minus of sin of omega t plus 120 degree plus phi multiplied by sin of. So, this is what you have now and you can see that this is actually an expression and these are all constants. Under a given operating condition you have a particular modulation index, a particular DC voltage and then you have a particular modulation index, then you will have a particular value of Vm and you will have a particular load and therefore, the peak current of I is Im and Ts is your subcycle duration. So, all these are constants now. Then this is at the time varying part and you can see that there are parameters coming here. This is what is that? this is the power factor angle phi, and this is 60 degrees, this is alpha. Alpha can be replaced in terms of omega t, you can say omega t is 90 degree plus alpha, as I just wrote a while back, and similarly here also you can replace that. So, this whole thing can be replaced in terms of omega t can be replaced in terms of alpha. So, you are going to get an expression in terms of alpha and phi, you are going to get an expression in terms of alpha and phi. This part is going to be a function of alpha and phi, and this part is going to be there. So, you can see that your IDC depends on various parameters. One is it parameter depends on the DC current, and excuse me, and there is the DC voltage, and then there is the modulation index Vm, and then the peak value of current and the power factor angle, and so on and so forth. So, you can deduce this expression. You can do a similar exercise considering sector 2 instead of sector 1 and check whether you come up with an expression. You complete this expression, which is just some more mathematics, and you try doing a similar exercise for sector 2 and see if you come up at this thing. This is something that you can just take it as a home assignment for this. This exercise will kind of help you correlate the DC side current and the AC side current better now. And you should understand that these 2 level voltage source inverter is one of the simplest configurations of voltage source converters. Here you should be able to relate the DC side and AC side better. Only then there are other applications, I mean there are multi level converters and so on, and in those cases you will be able to relate them in a much simpler fashion. So, this is a useful exercise in that regard, and you can just go about doing this now. Now, what we will do is we will try certain alternate ways of doing it. Now, I started off saying that after establishing this whole thing, that is writing down all the equations pertaining to the inverter model, I said we will take space vector modulation, and in the space vector modulation what happens, the entire fundamental cycle is divided into individual subcycles, and for every subcycle some reference vector is provided like this, and an applied voltage vector whose average is equal to the reference vector is applied now. So, you apply vector 1, 2, 0 and all for this time, and you can come up with that, and these are the times for which apply, and based on this we went ahead and calculated. We found out for every particular state what is the corresponding value of DC link current, and then the inverter state changes in a particular fashion, and so every time it changes we change the current, and IDC is now equal to IR, it is equal to minus IB and so on, and so you get these kind of waveforms here, and so we try to do this from that particular point of time point of view. So, this is more from the space vector modulation, it is from the space vector point of view, that is we have assumed it to be space vector modulated, or rather we are looking at this and then we are trying to derive here. So, we are looking at how the inverter state changes from one to the other. An alternate way of doing this would be to look at the modulating signals, that is let us say you go here, let us say you look at this, what is this SRIR, SYIA and SBIB. Now, this is the instantaneous value. Now, if you are looking at the average, that can also be determined by the average of these, correct. So, that is the other way of doing it. So, let us go to the end here, right. So, what we do is let us restart this exercise. Okay. So, what we have is let us start saying we have IDC equals SR IR plus SY IY plus SB IB. Now, both can be integrated 0 to Ts, 0 to Ts with respect to T, and you can divide by 1 by Ts on both the sides. So, when you do that, what do you get? This is nothing but IDC average, and what is that equal to? It is basically equal to IR multiplied by integral of SR dt 0 to Ts divided by Ts. Similarly, it is IY into 1 upon Ts 0 to Ts Sy dt, then IB times 1 upon Ts integral Sb dt 0 to Ts. So, what is this equal to? The question is what is this equal to? This is the switching function, it takes values of 1 and 0. So, when it is 0 the integral is not affected, whenever it is 1 that is only when affected, and so it is going to be 1 for certain amount of time, and what is that? That is really the duty ratio. So, that is really the duty ratio for which. So, it is on for certain duty ratio times TR. So, this becomes rewritten as dr IR plus dy IY plus dB IB. Is it right? So, you can write that in terms of the duty ratios, the time for which the top device is on. What do you mean by duty ratio of R? This is the on time of the R phase top device divided by TS. So, this is what you have now. So, you get this. This is for the time for which it is on, and when you that is, and similarly dy is the time for which the on time for the Y phase top device divided by the total subcycle time, and dB is defined similarly as T on times B plus divided by Ts. And this approach is useful and is very valid. So, what you can now do is you see that dr, dy, dB are all there. All this dr, dy and dB can be expressed as some functions. You already have IR, IY and IB, and IR, IY, IB can be approximated by IR1, IY1 and IB1 as I said before. That is their fundamental components. I am sorry, this is IB1. And the next thing is you can look at dr, dy and dB. And what are these? dr, dy and dB are also functions of the fundamental, I mean the change dr, dy and dB change with the fundamental angle. How do they change? That depends on the PWM method. So, if you are talking of sinusoidal PWM method, what happens is dr, dy, dB change in a sinusoidal fashion. So, you will have some way of writing this up. So, let us try doing that now. So, let us say we go to sinusoidal PWM now. In case of sinusoidal PWM, what do you have? You have your modulating signal MR equals Vm sin omega t. Is that right? This is what you have, and what is your duty ratio of R phase? This is something we had done in an earlier class now. So, you can now see that this MR would vary from -1 to +1 corresponding to your duty ratio variation from 0 to 1. This you can relate to the duty ratio. You can relate to the duty ratio. So, when MR is equal to 0, the duty ratio is 0.5. That is how you will get a relationship now. So, from here you can express duty ratio as a function now. Sometimes what happens, similarly from My is Vm sin of omega t minus 120, and from this you can express duty ratio as a function of omega t, and the same way you get Mb. Now, you may not use sinusoidal PWM, you may sometimes use let us say a third harmonic PWM or something else. So, you will have your MR star is some Vm sin omega t plus MCM, and this would give your duty ratio of R phase. So, the duty ratio of R phase is now a different function on the fundamental angle than it is now. So, what you can do is you can also evaluate this duty ratios of R phase, Y phase and B phase, and you can go about doing that. You can write this as sinusoidal function, Y as this and B as the other one, and from there you can come to this whole point, that is you can write this as some functions. Let me just write it down. So, IDC average equals dr IR1 plus dy IY1 plus dB IB1. This is a function of omega t. I will call this as Fr of omega t, and this is another function of omega t. I would call this as Fy of omega t. this is another function of omega t, I will call it as fb of omega t. Now, how about the other ones IR1? So, this also depends on the modulation index. So, this also depends on the modulation index. So, one way I can say that this is omega t comma m, also omega t comma m is omega a t comma m now, and this is a function of whatever the peak value I m, and this also varies with omega t and also the power factor angle r. So, let us call this not f, for example, let us call this as some g, let us call this as some gr, and this is some other function g, I am sorry, g y of these I m omega t and phi, and this is some g b of I m omega t and this power factor angle phi. So, this can be expressed now. So, this part is not dependent on the PWM method, this part is not dependent on the PWM method, they are just 3 phase quantities. We have ignored the fundamental component, I mean we are ignoring the harmonic components, the ripple, we are assuming that the ripple is much smaller than, so that's which is true in most cases in PWM inverters, and therefore, you can ignore them. Once you have ignored, it is only 3 phase currents, it is I m sin omega t plus phi, I m sin omega t minus 120 plus phi, I m sin omega t minus 240 plus phi. So, these are 3 simple functions now. So, what depends on the this PWM signal? This depends on the PWM signal dr, dy and dB, and this varies from one PWM method to another PWM method also. So, there will be some variations you must expect when you do these kind of studies here, but there are always some ways to say that there may not be a very significant difference. It may appear to you that the DC link currents are all very different when you change from one PWM method to another PWM method. I can very simply prove that it is not really so. I mean there are some variations, but the overall particularly if you look at it in terms of the capacitor DC link current, you will find that they do not vary significantly. What is more important is we must be able to get a value for that RMS current ripple, so that we can estimate that. It is not very it is not very much different. That may not be very apparent from here, because this suggests that these change with that, and we are not very sure how much it is going to change now. Let me tell you, if instead of these 3 phase modulating signals, if you go back and look at it as the inverter states rather than 3 phases separately, you look at it as a state, that is 3 phases combined together, you have that advantage now. Let me draw that for you now, right. So, let us say this is what you have in a subcycle, and let me say this is what you have, your T0, T1, T2 and T7. Now, what is going to change? The same same operating condition. So, the same operating condition basically means Vref and alpha are same, Vref and alpha are same, and the Im values are same, the fundamental currents, these values are all same, and Vref alpha are same, meaning T1 and T2 are same. So, this is what it is now. Here T0 and T7 can be equal. Instead of let us say conventional space vector PWM, I have some other harmonic injection PWM or something like that, and therefore, the values are slightly different. So, what is going to happen? Let us say T0 decreases slightly, T0 decreases slightly, then this is what is going to be, the whole thing is going to be shifted to the left a little. So, it is not going to change the average value, the instantaneous value of the DC link current is changing, but the average value of the DC link current over Ts is not really changing. So, that is the point that you have to note now. Let us say we go to bus clamping PWM method, not apply one of the 0 state at all, 0 is not applied, we use only 1, 2 and 7. So, let me look at it in a different color, write it now. So, if you are doing it like that, so this is going to become 0, it is going to be as indicated in the blue ink, this is sequence 1 to 7. So, this is a bus clamping method, but it is the same subcycle duration we are maintaining. So, here what do you see? The IDC average is unchanged with addition of common mode component. This is something you can really see. So, it does not matter. So, this is what you find. So, this is one reason why we look at many things in the space vector point of view. We need to do it in both versions. You need to be able to handle it like this and also able to handle it like that. But when you are able to do it in both different ways, well, they have their own relative advantages. If you look at it in space vector, the one advantage you are getting is you are able to see all the phases together, and that gives you a significant advantage now. So, this similar approach of DRIR etc., we will be using when we go to evaluation of switching losses or conduction losses. So, in conduction losses particularly, you will have 3 phase currents, and corresponding to every phase current there will also be some amount of voltage drop, and the average voltage drop in a device would once again depend on the duty ratio. So, you will see there is some similarity there. So, we will use that, we will do that in one module later, that is the next module we will be doing the torque ripple analysis, and the module after that we will do this now, but this kind of analysis will also be helpful now. So, today what we have tried to do is we have just tried to get a feel for this problem and how we can relate the DC link currents and the AC link currents, that is how do you relate the DC link currents and the AC side currents. We have just primarily got that now, and what actually remains to be done is basically to come up with this I cap. So, for this what we have to do is essentially we need to get a clear expression for IDC, and once you have this IDC average, you can what you can do is you can get a further average of this IDC over the sector, that is its periodicity, and that will give you whatever is the DC current, and this DC current flows from the supply, and we can assume the rest of the ripple to be flowing from here now. So, if you can plot IDC average first as a function of omega t for 60 degrees and get the average value of IDC average, this is IDC average is averaged over the subcycle. IDC average can be varied over a sector, you can get its average over a sector, and that gives this current. If you subtract this one from IDC average, you would get the corresponding I cap, and from there you will be able to evaluate that. This is something we will discuss in the next class before we go on to the module on pulsating torque. So, I thank you very much for your interest in this lecture. I hope that you found it helpful, and hope you would follow the next lecture, which is going to be on the calculation of capacitor signals and also the subsequent modules. Yeah. So, thank you very much.